Awesome. So this is quite a change of pace. So what I'm going to do is step through all of the magnetotelluric data and what that has to contribute to this story. So really quickly, first, for anyone who's not familiar with MT, it's an electrical geophysical technique. Sorry, I'll just get a pointer so I can wave it around at things. So it's one of quite a suite of electrical geophysics techniques we can use. It's really the only one that's going to be useful in a study like this. So if I think about the other kinds of electrical geophysics that we deal with, airborne EM, ground and hybrid-based EM systems, we're not going to get penetration down through past about 1 kilometre in Australia. But with MT, we can look down several kilometres, even down into the mantle, depending on how we acquire our data. So it's really the only technique we have in the electrical geophysical space to understand what's going on in the deep crust. So magnetotelluric data is sensitive to subsurface electrical and conductivity variation. A really nice thing for a study like this is the data integrates really well. So it's collected at single sites, and then you can combine several surveys or data from several surveys together, no worries. And sorry, let me just grab a drink. Something to keep in mind as I go through interpretation of all these structures is that the interpretations for magnetotelluric data are generally conducted on an inversion model rather than the data itself. So that means that we take the data, we put it through a numerical process, try and develop an understanding of what sort of structures underneath the Earth's surface will cause that data. And then we make an interpretation based on that model. So this elevates the uncertainties that we deal with a little bit from interpreting raw data, but it's really the most convenient path to a geological understanding that makes sense. So we've got a hell of a lot of data in the Mount Isa area. We've got over 3,000 sites. In the north of the province, so up here, we've got a wonderful backbone of some Auslamp sites collected by Geoscience Australia, and those are these green squares. And then in the smaller black points, we've got a variety of different MT data sets from a number of surveys over the years. So they fall into two categories. We've got a series of traverses, predominantly along the deep crustal seismic lines. And then we've got a couple of these big arrays that provide higher density data, better resolution, and a better understanding of what's going on in 3D. The sites that we're dealing with generally give us resolution into at least the mid-crust, often full crustal electrical data from these broadband and audio magnetotelluric surveys. And I think critically, one of the reasons that we keep doing these MT surveys along the deep crustal seismic is that the electrical properties and the acoustic properties of rocks are quite independent. So it gives us two lenses to look at the same rock through. So we generate a better understanding of what might be going on. So I'll start the talk up here, looking at the data sets around Cloncurry, and then I'll step through some of these historic transects and then move down into the south of the Mount Isa province. Really just focused on Mount Isa, not looking at how the relationships continue out into the Thompson or up towards Georgetown for the MT part. The two surveys that I've starred here were actually completed and released or will be released during the process, during the project. So the models and interpretations based on those data sets are a little bit more preliminary than the ones of the more established surveys. So I thought the best place to start was with the Auslamp model. So this is obviously work done by Geoscience Australia. if we look at the electrical structure from the Auslamp model, so this is a 33-kilometre slice out of that model, so mid to deep crust, we can see that there's really just a threefold division of the Mount Isa province. The electrical structure is a lot more simple than the seismic structure. So it just gives us a nice simple place to start and try and understand some of these higher resolution surveys. So we've got this beautiful linear resistive chunk in the middle of Mount Isa, and then on either flank we've got a conductive anomaly. So throughout the talk, resistive will be blue and conductive will be red. And so this conductive anomaly down the western side of Mount Isa is nowhere near as strong as the one down the eastern side. This structure on the eastern side of Mount Isa has a name. It's the Carpentier conductivity anomaly. It's really strongly conductive. It's a bit variable along length, and it's quite strike extensive as far as we understand. So it's a big structure. So I just want to note, as I step through the surveys, I've made sure that the conductors are consistently labelled. So it might be a bit of an ask to follow through as I step through all these structures, like electrical structures, but they're all consistently named. So if I talk about slides, that is the same structure.
We're losing your sound a little bit, Janelle.
What if I sit closer? Hopefully that's better.
Yeah, that's great.
All right. So as I said, I'll start up in Cloncurry. So up here we've got two different stages of a grid-based survey. So we've got this initial triangular section that was collected in 2016, and then we've got a really recent one collected and released in 2020, released in 2021. So the work on this survey is a bit more preliminary, but I can start by showing you the work from the 2016 survey. So again, modelling done in collaboration with GA. What I've done here is selected out a number of slices down through the 3D model. So starting from the near surface on the left and stepping down through to about 20 kilometres depth. This is probably the maximum extent of the resolution for this survey, partly because of data quality, partly because of the size of the array. So for the big scale structures in the project we're working on here, there's really only two features that are of great interest. There's this elongate conductive structure that wraps down the eastern side of the survey. It's present at all depth slices. And if you look carefully, you can see that there's a general expansion of this feature to the west as you get deeper. So it's probably a west dipping structure, and I'll show you a section of it in a minute. And then as we go down into the mid-crust, we've got quite a pervasive area of elevated conductivity. Certainly not the whole area at this slice, but as you get deeper, this whole area is underlain by quite a conductive lower crust, which is what you would expect based on the Auslamp data. So the next slide I'm going to show you is a section off the top end of this data. So this uses both that 2016 data and the new data collected and released this year. It's only a 2D inversion, not a 3D inversion, so the results are a little bit more uncertain. But with that caveat, you can still see that we've got a conductor that comes up to the surface, a large west dipping trend that merges in with this deeper conductor here in the mid-crust. And from these two surveys, that's really the major takeaway for a project of this scale. There's a lot of smaller, more interesting superficial anomalies that might be, that are worthy of follow-up study, but not relevant to this work. And then the other way that we can slice this data, so instead of just looking at MT in isolation, we can extract a series of sites that are parallel to this, the deep crustal seismic, and then do some modelling based on those sites. So that's what I've done here. So I've got the interpretation that we generated for this project, and then a comparison of the major features with the magnetotelluric data overlaid on the seismic. And this is where I'm going to start labeling up these features, and there's going to be a few come in, so hopefully we can all keep track of them not too badly. So C1 you've already seen, that's that shallow conductive feature along the eastern margin of these surveys here. In this inversion, we can see that it actually extends quite a long way east. Interestingly, it seems to be confined below the Malungara Basin. So these reflectors here are the Malungara Basin, and then immediately underlying that, we've got an indication that there's something conductive inside the Soldiers Cap group, which is this white unit here. So that's C1, and then looking at C2 and C3, they seem to be part of the same structure on this section. I promise you there's a bit of difference. So C3 is the most conductive part, and it's associated with quite strong reflectors in this deep crustal seismic. So it's possible that it's intimately associated with the Gidgee structure itself. And then C2 is generally a broader area of mid-crustal conductivity. And then R1 is the expression on this line of this big resistive block that runs down the center of Mount Isa. So we can see it encroaches quite far west in this inversion result. Other inversion results say it doesn't quite come this far, but it is here regardless. So if I look at these, just these three historic lines, again, I've selected ones that compare to the seismic because I think it's a lot more instructive. So CF1 is probably the most difficult one to understand. We're sitting up here with a northwesterly strike and crossing straight over the top of this very large lower crustal conductor. What we can see is a massive call out to Wen Peng down at GA. These inversion models that I'm showing on the next three slides are her inversion models, not mine. So this is from some published work a couple of years ago. I've taken those models, overlaid them on the seismic, and then compared them to our interpretation so we can see what those structures might mean for our interpretation. So C1's popped up again here on this seismic. So again, associated with the Soldiers Cap group. So there's something conductive sitting in the Soldiers Cap group and potentially extending down further into the Numel. There's a missing piece of conductivity here associated with this granite that could be related. So there's something different about this part of the Soldiers Cap group, probably the intrusion of granites. And then we've got potentially, if you squint a bit, maybe some elevated seismic reflectivity associated with this central part of the anomaly, which is similar to C3 on the previous line, which was IG1. And then we've got a new structure that's popped up here. So this one sits up here off the northern end of the CF1 line. It's associated with at least the Leichhardt superbasin and potentially the underlying central Isa block. And I'll go into some arm waving about what these things might be at the end. So bear with me as I step through and show you what they all look like. So the next one in these set of parallel seismic lines is M4. Again, our interpretation at the top and the electrical structure on the seismic. And this one seems like quite a really good fit to our interpretation. So this would be the location of the Gidgee structure, and so that's replicated here in these black lines. And you can see that it's not perfect, but there is quite a good alignment between the location of this dipping conductive structure and our interpretation of the Gidgee suture. So it seems like this really strong, very conductive response is probably tied quite intimately to the Gidgee structure. But then we can step further south again. So this is M6. We're just on the edge of the constraint that we can have from the Auslamp model. We don't have, well, we didn't have sites down here, but we have some brand new sites that haven't been modeled yet. So we don't have any control on the deep structure, on the deep electrical structure down on this line and all the following surveys I'll show you. But we're quite close to the model, so we can expect that a lot of these structures will extrapolate down into the area. So if I compare again Wenpeng's model to the seismic and our interpretation, it looks like a very different thing to what's going on in the north. So this here, this bendy line is the Gija suture down here. We don't see a strong conductor associated with this southern extension of the structure. What we have instead is this new form where we've got a very large area of moderately conductive lower crust, largely confined to the east of the Gija suture and potentially links with some of these shallow structures through some major faults. So that's interesting. Obviously something has changed down here. We've got an introduction of a couple of new features. This guy down here contained within the eastern succession, C7, is associated with these very strong reflectors. And then C6 is a bit larger, a bit less well connected to the seismic character, but definitely has a potential linkage down along some of the faults. We've got an expression of the resistive block down here, which we would expect it to continue. It's quite a long belt. You would expect it to continue further south. There's the start of a hint that it's actually associated with the Pitta block, and certainly the location of it further north does trend the same as the Pitta block. And then creeping into the western side of this survey of this seismic line, we've got we're starting to see the expression of this western conductor that runs down the western side of Mount Isa. So it's not very compelling here, but we're only just clipping the very edge of it, so that's expected. So that's a lot of structures. So it's quite a complex story. This is all the structures. So if I whip through them with a map view, hopefully they'll make a bit more sense. So we've got C1, which was that broad area of conductivity associated with the Soldier's Cap group. So this is the Gija suture here in black, and it actually sits out here on the eastern side of that suture in the shallow crust. And then we've got C2 and C3, which seem to be intimately associated with the location of the Gija structure, but only really up here around Cloncurry. As we continue further south, we don't seem to see that really strong conductor continue. C4 is a bit of a weirdo thing that just happens on CF1, on the very northern end of CF1. Doesn't appear to have that much to do with any of the other structures, other than the fact that it's currently imaged as an enormous blobby mass that joins into some of the other ones. So C5 doesn't exist in the north, but does in the south. So we pick up C5 as a broad, lower crustal, moderate conductor on M6, and I'll show you that it continues further south onto CF3 in a minute. And then we've got a couple of near surface conductors, so that's C6 and C7, again, only really on M6. And they sit in here through the central part of Mount Isa. And then we've got this western succession conductor, and the lone resistor that I care about, apparently, is the Pitta associated resistive block that runs down through the center of Mount Isa. So if I step down to the two surveys that we've got in the southern part of Mount Isa, I've got the Isa Extension Survey, which is this big array here, and then a series of sites that have just been collected along the CF2 and CF3 seismic lines. I'll just be showing CF3 today. But important to note, there is no Auslamp modelling available for this area yet. I'm sure it's coming, but we can use these broadband surveys to try and help us extend these features down into the south of the Mount Isa province. it is quite deep and quite concealed down here. So there's quite a lot of cover for anyone who's unfamiliar with this project area. So it's not as immediately obvious how some of these things might link to the outcrop because we simply don't have any outcrop. So there's some 3D modelling available for the ISA extension survey, and this is work that I did a number of years ago now. But there's really only two features of interest here for this project. So what I've done is just taken a depth slice out of that 3D model, and you can see the eastern side of the survey, there's a massive resistive block, and on the west, there's a slightly complex, moderately conductive structure. So this is very consistent with what we see just to the north of the survey. So it looks like this big resistive block down through the middle of Mount Isa continues south into the Isa extension array and potentially swings around a little bit in orientation to head off to the south-southwest. This slightly complex feature merges into a single feature a bit deeper and is almost certainly a continuation of this western succession conductor down into this project area. And then finally, looking at what the data along CF3 can tell us. This is brand new data and hasn't been released yet, so I promise it'll be released soon. But I think it's worth showing because it is strikingly similar to what's going on M6. So we've got pretty much exactly the same structures here. It continues a bit further to the east, which is helpful, and it also continues a bit further to the west, again, quite helpful to better understand the bigger context of what might be going on M6. So stepping through from C1 wasn't imaged anywhere on M6, possibly because it doesn't come far enough east. So there's a suggestion, but on this one, we've got a big block of Soldiers Cap group interpreted. Again, we seem to see a very shallow, quite conductive layer here inside the Soldiers Cap group that could be a continuation of what's going on outboard of to the east of Cloncurry, I should say. So that's interesting. We've got a big, broad area of moderate resistivity underneath the Gidja suture. So this guy here is the Gidja suture in this interpretation. So this is very similar to what we see on M6. Again, we've got a shallow conductor associated with some very strong reflectors inside the eastern succession with potential linkages down to this deeper conductor. This structure here is a little bit difficult to resolve in 2D inversion for this line, but it typically comes out as some sort of conductive feature associated with the central Isa block, which is this pink block, connected through faults down to the deeper structure again. This one is not as compelling as a lot of the other sections. So I've done several inversion tests on this data, and this is probably an atypical result in the west, but it's a very typical result in the east. So I think these structures here are very well constrained and very two-dimensional. And then this structure here, C8, moves around a lot as you model it. So it's quite three-dimensional. So it probably needs follow-up modeling to understand where it is properly. But regardless, it seems to be generally associated with either the western flank of the Pitta Pitta block or just off the western flank. So in this block here. And the Pitta Pitta block is generally very resistive. So it's a simpler story in the south. We've got less structures down there. We also have less data, so maybe that's not reality. Maybe there's more structures hiding that we're simply not aware of yet. But we do seem to have a continuation of the C1 structure down here to the east of the Gidja structure, which is potentially a continuation of what's going on up here around Cloncurry. And then we've got this large, moderate conductive structure that sits in the lower crust in the normal terrain. And then 5 and 6, C5 and C6 are smaller, more isolated anomalies in the mid to upper crust, potentially with linkages down into the lower crust, same as M6. And then we've got the western conductor and the central resistor, R1. So hopefully I haven't lost anyone. That's a lot of structures to whip through, a lot of inversions to look through as well. So if you've got any questions, I can go back and answer them hopefully. But it's one thing to catalogue all these structures, then you probably want to think about what they actually mean. So when I'm thinking about interpreting my MT anomalies in terms of geology, I kind of have this very broad split into two camps where I've got anomalies above 10 kilometres, anomalies below 10 kilometres. So above 10 kilometres, the story's a bit easier. When you're looking at conductive anomalies above 10 kilometres, you're probably looking at compositional variation. There's not as many factors that can influence conductivity in the shallow crust as there is in the deep crust. So up there, really compositional variation. So you're talking the presence or absence of brines or groundwaters. Massive sulfides are obviously quite important in the Mount Isa area, as are graphitic schists. And they're the primary candidates that I think about when I'm trying to understand what these anomalies might be in the shallow crust. Obviously, these are very conductive compared to general country rock. But as you go deeper into the crust, things get a bit weirder. There's more factors that you have to think about. So there's things like variations in temperature can cause elevated conductivity, increased pressure, so like tectonic stresses can elevate your conductivity, fluids can do it. So anything that flows, I'm talking fluids in the deep crust or potentially magmas, anything like that. Probably not that relevant in Mount Isa, but something to consider elsewhere. And then the other one that comes up quite regularly is hydrogen. So that's a weird thing to think about, but the way I think about it is essentially hydrogen is a proxy for fertilization by fluids moving through the crust. So all of these factors plus composition are things you have to consider when you're looking at anomalies in the deep crust. So these are just preliminary hypotheses. They can and should be tested more rigorously than I've managed to so far, but who doesn't love a bit of arm waving? So I'll whip through and give a possible interpretation of all these conductive anomalies and see how we go. So starting at the start, the C1 conductor. So as I've said, it's really contained within the soldier's cap group. So something to think about with this conductor is that we probably don't have a very good control on how thick it is. It's part of the nature of MT data that a very thin, very conductive layer will model very similarly to a broader, less conductive layer. So this could be a very thin, very conductive unit within the soldier's cap group, or it could be this broad anomaly that you see here. Interestingly enough, it doesn't seem to have a consistent seismic character across the entire area, but it is definitely restricted to below the Malungra Basin. So because we're in the top 10 Ks, it could be some sort of saline brines in the metaseds, or it could be a graphitic shale layer somewhere in there. So both of those I would expect to be a lot narrower than this anomaly looks in the modelling so far. So next structure, I've grouped C2 and C3 together because they both seem to be associated with the Gija structure. C3 is not very extensive, like it's only really captured well on one of the sections, this one here. So, and it seems to be very associated with some very reflective layers. So in other studies, it's been suggested that this kind of highly reflective, highly conductive layer associated with a suture could be some pentonized units associated with the suturing itself. So that's a possibility here. And that's the best I've come up with so far. C2 is probably a more likely candidate for hydrogen fertilization through fluid movement along the structure, because it's not quite as highly conductive, doesn't seem to have a consistent seismic character, and is a bit more broadly distributed. Whether or not hydrogen fertilization is enough to explain the strength of this anomaly is something that warrants testing, hasn't been done yet. This little isolated conductor on in the very far north is a bit of a difficult one. I haven't given it a lot of consideration because it's not as interesting as the others, I decided. So again, I think we're probably in a situation here where the thickness is uncertain. It looks like it's a very thick package on the current inversions. It doesn't have a consistent seismic character. So on this model, it looks like it not only is in the Leichhardt superbasin at the top, but down into the underlying central Isa block. This could be true. It could be a smearing of a very thin conductive layer. Again, it's probably a compositional anomaly potentially associated with faulting, but I would have to do more looking to work that out. Probably graphitic or sulfidic related anomaly. So stepping down to the south, where we've got this broad area of moderate conductivity in the normal terrain. This is not superconductive, but it is moderately conductive. It's possible that we're seeing simply a compositional difference between this block of crust and the adjacent one, which is the pitter block. So that would explain the difference in the lower crustal conductivity. It's also possible that we've had a lot more fluid flux through the lower crust in the east, which could potentially be related to the intrusives that are filthy throughout the eastern succession. So for C6 and C7, these are definitely mid to upper crustal conductors. So again, thinking about composition, but they do seem to have connection down to the deeper conductor along some faults. So it's possible that we've got some compositional contribution, but also some preserved fluid flow through some of these faults, elevating the conductivity in these areas. Got a little note here that maybe C7 is the same as C4 on the northern lines. I don't know if it's true, but it's something to think about. And then the last conductor is this C8 conductor down the western side of Mount Isa. This one, I think, needs a lot more work to understand. The inversion models of it are quite variable at the moment, and that's probably got something to do with our current data coverage. My intuition is that it's a west dipping structure. It's most likely located on the western flank of the pitter block, but not in the pitter block. More modelling is needed to confirm that. And it's a continuation of the structure further to the north. So hopefully as we get more Auslamp data down to the south, we'll be able to get a better handle on what the deep structure is, and then some 3D modelling of the CF23 MT data that is to be released soon will help give us a better feel for the character of this structure. But again, it's not massively conductive, so maybe we're seeing a compositional variation between the central part of Mount Isa and the western part in the lower crust. And then we've got this big resistive chunk through the middle. It is quite closely tied to the location of the pitter block and could actually be the expression of that block. A reason for its elevated resistivity is potentially it's of higher metamorphic grade, it is really dense as well from the gravity modeling, so it does seem to be resistive and dense. So maybe metamorphic grade is a good interpretation. Otherwise, maybe there's just not been any fluid flow up into the lower crust here. So it's worth noting from the Auslamp data, this resistive block does extend down into the mantle. So it's not just a crustal structure, it's quite a significant thickness of both resistive crust and resistive mantle that is continuous. So that's where we got to with this project. There's a bunch of ongoing work planned, including all the 3D inversion I've been promising, and there's acquisition of a new data set down the eastern succession of Mount Isa that we're planning at the moment. Hopefully it'll get underway middle of next year, and then that'll give us a better backbone for understanding what's going on between the really conductive part of the Carpentaria conductivity to the north, conductivity anomaly to the north, and then the less conductive, more diffuse anomaly we see on M6 and further to the south.